Okay, Assalamualaikum warahmatullahi wabarakatuh. Let's say we have one charge here. So this is not the question, but maybe on apa, one type of the question lah, right? So let's say we have two charge, for example. Okay, so this one is maybe cover for the second type of question, right? So when we have a charge here, so basically each charge will be produce its own electric field. So let's say flowing outside. Okay. So let's say we put one test point here. Okay, our test point. So this is our P point. And we need to determine the E here, for example. Right? So how can we determine the E here? So basically we need to establish our vector, right? So R1 and R2. Okay, let's say lah. So this is our condition. So let's say uh, if you put another uh, charge density here in the line, for example. This is our rho L. So what happened to this E? Okay. So maybe kot this is sample of the apa nama or the macam contoh-contoh soalan lah kot. So maybe this is the coordinate given for this question. So maybe x1, y1, z1 for example. So this one maybe x2, y2, z2 for example. So this maybe we will given the rho L in term of some expression, full information. So maybe something like this but actually the question is not ready yet. So I also don't know the style of the question. But the style of the question maybe almost similar what you already answered in the exercise. Right. So basically you are not you don't need to remember all the formula or the step of the derivation, so on and so forth, because you can always refer to the note, you can refer to the book, but the thing is you need to know how to apply that particular question regarding on a specific problem. So the one is more important lah, okay, rather than memorizing the equation and step. All right. So perhaps maybe you got one or two questions that we can discuss. Kan, mana dah tahu kan soalan tu mirip-mirip test ke. Since the test question is not ready yet kan, why not? Mana tahu kan daripada soalan awak tu timbul idea nak buat soalan ke. Okay, so this one is for the long question lah. For the short question, uh, maybe it's some question like how to say. So let's say we have one pattern of uh, field, for example. So let's say this is the field pattern. Okay. So this is one vector lah. So vector V, for example. So let's say we are performing um, divergence of vector del dot V, for example. So what is the answer if we have this kind of vector? So what is the answer when we perform this one? Okay. So the one is for the short answer lah. This one or so let's say uh, if we have one charge if we change the medium of the charge, for example, okay, so we want, so we put this the same charge in another type of medium, for example. So what will be the what is the effect for the value for the electric field intensity, for example? Okay, so that is the question that make you or need you to make very fast or very short uh, short analysis or short decision. Okay, so let's say we want to achieve E is equal to how many volt per meter, for example. Alright, so and given us the E is equal to how many um, epsilon, for example. So what is the value of the Q? Okay, so based on this uh, based on this apa nama equation, something like that lah. Okay, because in E, so let's say we are based on the Coulomb's law, so it's 1 divided by 4 pi epsilon, so multiply by Q divided by R squared, right? And the unit vector for it is equal to R cap. Okay, so some of these elements will be constant. So for example, this is a constant value. So what will be happen to the value of E is some of the constant, especially in terms of epsilon, is changed, for example. Right? So it's something like that lah in terms of the short question answer. Okay, so maybe you need to make a very intensively calculation, but from the first glance or first point of view, then you need to make some evaluation. Tutorial 3, question number 11. Right, so this question is regarding Gauss law. In certain region of space, the charge density is given in a cylindrical coordinate system by the function rho v is equal to 5r e power of minus r exponential power of minus r coulomb per meter cubic. So apply Gauss law to find E. Okay, so we have rho v is equal to 5r e minus r coulomb per meter cubic. Okay, so we need to find the expression for the E. Alright, so basically, so we have two method lah to solve this one, okay? Because under Gauss law, basically we will have del dot D is equal to rho v. So this one is differential form of Gauss law, right? And then we will have another form which is closed integration of surface D dot ds. So this is equal to Q. Okay. So this one is integral form. Okay. So in order to solve this, okay, so let's consider the integral form first. Okay. Let's say we are trying to solve this equation by using this first. Okay. So basically, the question gives us the charge density is given in cylindrical coordinate system. Okay. So we need to apply cylindrical coordinate system. Okay. In a cylindrical coordinate system, so we will have the component of r cap, phi cap, and z cap. Okay. So the shape for the cylindrical is something like this. So this is the shape for the cylinder. So to solve it, so let's say that we have our general expression for the D, so the vector of D here. The vector of D is equal to r cap multiplied by dr. Okay, and in this case, the equation for ds so should be include the top, bottom, and the side surface. Okay, so how can we get the expression for the general expression for the vector of D in a r cap direct in a r cap direction? Okay? Because so normally when we talk about charge that present in a line charge density, okay? So we will have cylindrical shape. Okay, and most of the time, so basically the direction of the electric field will be developed in this way. Okay? And since basically we have expression or relationship between D is equal to epsilon multiplied by the vector of E. So from this expression, so we know that basically the direction for the vector of D and direction for the vector of E will be in the same direction. Okay. So if we have the direction of E or the field in this direction, so the same goes to the direction of the vector of D. So because of that, so we can assume that our general expression for the vector of D is equal to r cap multiplied by dr. So dr is the amplitude for the uh, electric flux density. Alright. So at the same time, so we need to perform a close integration, close integration of area. So we need to perform a close integration of area. So whenever we have this operation, so that means that so we need to perform surface integration, okay, and add all together the result of it in terms of top, bottom, and side. Okay, so if we are referring to the cylindrical shape of a field, okay, so that means that so we need to have integration on the top surface. So this is the top surface, okay, of the cylinder. Then we have the bottom surface of the cylinder. This is in this side. So this is will be the bottom. And also we need to perform the integration in the side surface. Okay, the side surface will be this side. Okay. So because of we having deal with the cylinder coordinate system. Okay. So let's see how can we derive it. So close integration of d dot ds, okay, is equal to on the top surface. So this is our top surface. So the top surface will be in direction of z cap. So we will have surface integration of the expression for vector d is still the same. So r cap dr dot is surface that uh, that in a z cap direction. So we have z cap here, and because of z, so the parameter that we change is in dr and phi. Okay, so this is the expression for the top surface. So plus on the bottom surface, so this one will be on top. On the bottom surface, so we need to perform a surface integration on the bottom. Okay, so for the bottom surface, so we will see that so this surface will be in a minus z cap direction. Alright, so we will still have the same expression for the vector of d. Okay, but for the ds will be in direction of minus z. So r dr and d phi. Okay, so this one is for the vector. And for the side surface, okay, in this side surface, so the side surface, the direction of it in r cap direction. So because of that, so we will have plus surface on the side. So the expression for the vector of d, we will have same expression. So r cap dr, and expression for ds will be in the r cap direction, d phi n r d phi n dz. Okay. So if you look into this equation, so we see that, okay, for example, on the top surface, so we need to perform a dot product between r cap component and z cap component. So definitely when you perform this operation, then we will have the answer for this part is equal to 0. Okay, so same goes to this part as well. So we need to perform a dot product between r cap and minus z cap. So of course this part also will become 0. And the equation that left with us is only on the side surface side only. Alright. So therefore, so we can have the equation that involved in this operation is only on the side surface. We need to perform double integration. So because we deal with surface, so r cap and r cap, so we will have is equal to dr, okay, multiply by r, d phi and dz. So in terms of the limit, so phi is equal to 0 until to pi, okay, because we are considering a full structure of a cylinder, and z is from 0, 0 until, so they didn't given us any information on the z, okay, so okay, we just take a is equal to z, okay. So if you solve this one, then we will have dr is dr to multiply by r. So the solution for phi is equal to 2 pi and z. Okay. So the unit of this is coulomb, right? So because of we are performing this operation, so the result for this operation is equal to value for q. All right. So this is uh, on the left side of the equation. All right. So let's solve the right side of the equation. Okay. So we will have the Q is equal to the volume integration of OV dot dV. Okay. So because the charge here is given in a volume density, right? So when we have to perform a volume integration, so we need to perform triple integration. Rho V is equal to 5 R E with the power of R, and dV in a cylindrical coordinate system is equal to R dr d phi and dz. Okay, so we have limit R is from 0 until I will just take until R. So phi is from 0 until 2 pi. Okay, the full cylinder structure, and the z is from 0 until z. Okay, so if you solve this one, okay, if you solve this one, then we will have, okay. So the solution of it is quite long. Okay, because we have this expression. Okay, so we have this expression. Okay, so for example, in order to solve integration of phi and z, so the solution of it, then we will have equal to 2 pi z. Okay, because we didn't have any term of phi and z here, so definitely we will have 2 pi z here, right? So multiply by pi, and basically you need to perform this integration. So r equal to 0 until r, so r e minus exponential is the power of minus r, so dr. So this one will be r squared. Okay, so because we have term r here, and we have term r in terms of the equation here. So we have r squared. Okay. So in order to solve this, so basically you need to perform part by part integration lah. Kan? So kalau if you still remember, so you have u is equal to, we say r squared, okay, and then v is equal to exponential minus t and dr, right? So then this one you need to make du over dv. So this one you need to integrate to get what is the whatever the solution for this. Okay, but the thing is, in order to simplify the answer, okay, because of during that time you can refer any apa nama, any source, so you might see from one website. I don't remember the address of it. So let me find it. Maybe integral calculation. Integral calculator. Yes. So you just log in to www.integral-calculator. Dash calculator.com. Then you will get the answer for this question. Okay. Then after that, so once you get this one, so ada kawan yang bagi integral calculator. So once you get this one, then you just put it together again. Jadi 2 pi zr dr. Okay. So on our left side we have dr dot r 2 pi z. Okay, 2 pi z. So 2 pi z is equal to, so the solution of this lah. Okay, 10 pi z, and the answer for this integration, so r equal to 0 until r, so r squared e power of minus r dr. Okay. Then we just solve this equation, then we have the expression that represent our, so dr is equal to what, berapa lah. So and last kali what we should do, therefore so the vector of d is equal to r cap to dr. Okay, so this one is, if you solve this equation, so by using integral form of Gauss law. Alright, so let's look, so how can we solve this question if we are using differential form for the Gauss law. Alright, so in the differential form, so we have del dot vector of v is equal to rho v. Okay, so as similar like before, so the general expression for d is equal to r cap dr. Okay, then if we perform this operation, so when we have deal with the cylindrical coordinate system, so the equation for del dot d is right. So the equation of it is will become 1 over r d over dr dr, dr. Okay. So this one should be so plus 1 over r d d phi a phi plus d dz system of az. Okay. So this is the equation for the del dot sum vector. Okay. So if you are using the symmetric coordinate system. So in this case, so we can really see that basically the component of the vector of B is only exists in the r cap component. So that's why for these two components, so we can regard it as a zero. So we will have so del dot B is equal to 1 over r d dr. Okay, so r multiplied by dr. So this is will be equal to our rho v. So the answer, the value for rho v is equal to 5 r e minus r. Okay. So in order to solve this one, so we need to perform integration. Okay, for both sides. Okay, so first, before we can integrate these two parts, so we need to take this r, okay, into this side. Then we will have d dr r dr is equal to 5 r power of 2 e minus r. Okay. Then we need to perform integration. Okay. So we need to perform integration of the r. Okay. So for both sides. So in this side, so we have derivation. So when we perform integration on this side, so we will have r dr. Okay. So here, so we need to perform integration from r is equal to 0 until r 5 r squared e minus r dr. Okay. So same again. So in this case, we need to perform uh, integration part by part. Okay. So because of we have r squared and e power of minus r here. So that's why we need to perform part by part integration. So we can refer to the same website to get the solution of it. Basically, I think we have the same expression, right? Yeah, the same expression as previous one. If you can solve this one, so then you can solve this one as well. Okay, so in the end, so because of we have RDR here, and this is when you solve it, then you get one expression, okay, to represent the solution for this integration. Then you can have our expression for the dr. Okay, is equal to what? I think in this, yeah. So we have the answer for this. Okay, so based on whatever given in the as given in the tutorial, so we will have the vector of D is equal to r cap 5. So we have 2 divided by r, 1 minus exponential minus power of r, 1 plus r, minus r e. So this is the answer given in the question lah. Basically, I've done it before, but somehow all the material in my office, so I couldn't check. But I think I get the same answer as well as the answer given in this tutorial question. Tutorial 3, question number 1. So I think this one is the most simple question lah to understand about the charge density. Alright, so a Q2 meter on site is located on the first octane in the Cartesian coordinate system. This one of its corner is at origin. Find the total charge contained in the cube if the charge density is given by rho v is equal to y squared exponential power minus e minus 2z. The unit is millicoulomb per meter cube. Alright. So let's see how can we solve this question. So, so in order to solve it, so we have Q is equal to volume integration of rho v dot dv. Okay. So because we will performing volume integration, we need to perform a triple integration, right? So rho v is given by this expression x y squared e exponential power of minus 2z, right? So and this should be times power of minus 3, okay, because we have limit here, and dx, dy, and z. So for the limit for the x is equal to 0 until 2, okay, because the question say that the length of each side is equal to 2 meter, and one of the corner of his corner is at origin, right? So y also is from 0 until 2, and the z as well is from 0 until 2. Okay. If you solve this one, okay, so let's say we are start from the x first. So x is equal to x power of 2 divided by 2. The limit is from 0 until 2. Okay, and then y is the solution will be y power of 3 divided by 3. So the limit is from 0 until 2. And for the z, so we will have the same expression. So we have e minus 2z divided by 2. And the limit is from 0 until 2. Okay, all of it in millicoulomb. Okay? So because we have a power of multiplication of 10 of power of minus 3. Alright, so if you solve this one, then we will have 2 power of 2 is 4 over 2 dot with 2 power of 3 is 8, 8 divided by 3 dot with, so this one, this part of the question, the exponential with power of 0 is equal to 1. 1 minus e minus 2 multiplied by 2 divided by 2. Okay. So 16 divided by 6 now minus e power of 4 divided by, okay. Kalau selesai ni dapatlah. So how many millicoulomb? Okay. Spherical volume of radius A, radius A, radius A, okay, so contain a uniform volume charge density rho v. Use the Gauss law to determine 4R is less than A and R greater than A. Okay. So let's say we have one spherical volume charge density. Okay. Like this, so we have rho v. So use Gauss law to determine V for R less than A and greater than A. Okay, so we have this spherical shape with radius of A here. So we need to find the expression for the B, okay, for at the inside of the charge and outside from this charge. Okay. All right. So because of we deal with the spherical shape, so we will have, okay. First, the equation of Gauss law is like this. So, cross integration of surface d dot ds is equal to q. Okay. So in this case, so the value of 2 is represent by using its volume charge density. Alright, so before that, before we can solve this, so let's assume that if we have our general expression for the vector of D is in terms of r cap dr. Okay, because whenever we have a spherical shape of the charge, so basically the direction of the field will be in terms of r cap direction. Okay, and by considering this is a spherical coordinate system, so the expression for the surface ODS is equal to r cap r sin theta d theta d phi. Let me check first the ds. Where is expression? Okay, so dsr equal to r squared. So this is we have r squared sin theta d phi and the plot the d theta. All right. So then we can put all the information that we know together inside this expression. Okay. Because of we in this spherical shape, so we only have one surface. So that's why we have to make only single step of integration. Okay. So double integration of r cap dr. Okay. So this is the vector for ds. So r cap r squared sin theta d theta d phi. Okay. So the limit is first theta is 0 until pi and the phi is 0 until 2 pi. Okay. So if you solve this one, then you will have the answer for it is equal to, okay, so dr. Then we have r squared here. So r squared. So integration of sine theta, okay, with the limit from 0 until 2 pi, then we will have 2. And then integration of pi, okay, because of we didn't have any term of pi here, so we will get 2 pi. So the result that we will get is equal to 4 pi r squared multiplied by dr. And so this is the solution for this side of the equation. All right, so let's look on the solution for this part. Okay, so this part of the solution, which is rho v. So if we have the rho v, so in order to find the total charge enclosed inside the rho v, so we need to perform a volume integration. Rho v dot dv. Okay, so because of we need to performing a volume integration, so we need to perform triple integration. We need to perform a triple integration. Okay, so we just put integration first, so rho v and dv. So we will use the dv that represent our spherical coordinate system. So r squared sin theta dr d theta and d phi. Alright, in order to put the limit, okay, so first we need to we see the first limit first in terms of R. Okay, so for the area of in order to answer the first question, okay, when we have the R is less than A, okay, so that means that the value of R will be exist from 0 until any point inside this A. So we need to integrate this from A, so from zero until any R, okay, which is located inside this chart. Then the theta, the limit of the theta is equal to 0 until pi by considering the full structure of the cylindrical. So the phi is from 0 until 2 pi. Okay. So when we solve this one, so we will have rho v. Okay. The solution for r is r power of 3 divided by 3. So the limit is from 0 until r. Okay. So integration of sine theta. So we will have minus cos theta. And the limit is from 0 until pi. And we have phi. And the limit is from 0 until 2 pi. So we will have the answer for it is equal to so we have rho v here. Solution for this we will have r power of 3, so divided by 3. The solution for this is equal to 2. So the solution for this is equal to 2 pi. If you solve this together, then we will have 4 pi divided by 3 multiplied by rho v and r to the power of 3. Okay, the unit is coulomb. Okay, then 4 pi r squared dr. Then we will have 4, 4 pi r squared dr is equal to 4 pi per 3, 4 pi divided by 3 rho v and r is the power of 3, right? The power of 3. Then in order to find the expression for dr, so dr is equal to, so this the 4 pi can be cancelled out each other. So we will have so rho v r power of 3, so divided by 3, so multiply by 1 over r square. So we will have rho v, so r divided by 3. So therefore, so we will have the vector of d is equal to r cap, so rho v r divided by 3, okay, coulomb per meter square. So this is area that cover r is less or greater, less or same with 2. Alright. So based on the equation that we have, the question that we have, so we need to also determine the expression for the vector of d for the area r greater than a as well, which is this case is in the area outside uh, from this charge. Okay, so basically in this particular case, in terms of solution for the r, so we have Gauss integration d dot ds is equal to q. Okay, and basically for this side of equation, so if we solve it, then we will have the same answer. So we have dr multiplied by 4 pi r squared. Okay, but the solution for this side, so we need to do like this. Alright, so we have q is equal to volume integration rho v dot dv. Right, so we have still have a triple integration. So we have rho v and dv is equal to r squared sine theta d dr. So dr d theta and this d phi. So in this case, so if you remember, on the limit for R, so we need to perform in previous case R from 0 until R. Okay, because of in a previous question, okay, so let's say we have charge here, and the radius for that particular charge is equal to A, and we need to find the total charge that exists inside this radius. Okay, so maybe the R value is considered from 0, for example, until here, for example. Okay, so this is our R. So that's why we need to perform the integration, the limit for integration from 0 until any R, as long as the value of R is less than A. But in this case, so we need to consider the area that cover R is greater or the same as A. So in this case, so the area that we are searching is located in outside for the charge. Okay. So however, so we only have charge within the radius between 0 until A only. So that's why in this case, in order to determine the limit of this charge, so we need to perform this integration from 0 until A only. Okay, so by considering this, the radius of charge is only uh, with a value of 0 until A. Okay. So in terms of the limit for the theta, we still have 0 until pi, and the phi is 0 until 2 pi, okay, because we are considering a full shape of the spherical. So this one is rho v. And to solve this one, so we will have rho v, so r squared. So we will have r power of 3, so divided by 3. So the limit is from 0 until a. Okay, so integration of sine, we have minus cos theta. So the limit is from 0 until pi. And the phi is from 0 until 2 pi. So if you solve this one, then we will have uh, rho v a power of 3. So 2 pi is 4 pi here. So divided by 2. Then if we equal the both side, okay, so we have dr 4 pi r squared is equal to this formula, rho v 4 pi a with the power of 3, so divided by 3. Okay, so the 4 pi can be cancelled out each other. And we will have the expression that represent our dr is equal to rho v a power of 3, so divided by 3 r squared. So the vector of d is equal to rho v a power of 3, so divided by 3 r squared. So this unit vector is r cap, and the unit is centimeter per square. Okay, so based on the answer that we have, so basically we can rewrite our expression for the vector of d. So we will have the vector of d is equal to rho vr divided by 3. Okay, so rho vr divided by 3. So this one is region r less or same as a, and for the outside of the charge, we will have rho v a squared a power of 3. So rho v a with the power of 3, so divided by 3 r squared. So this is the region r is greater or the same as a. Okay, for the question B, if rho v is equal to 5 microcoulomb meter power of 3, and the radius of sphere is 5 centimeter. Find the electric flux density at 8 centimeter from the center of the radius. So this one is based on whatever that we have here. So we just put all the parameter that we know inside that equation lah, right? And since we have two regions, right? So we have two regions. So just now the information that give to us, so we have rho v is equal to 5 microcoulomb. So 5 microcoulomb per meter cubic. Okay. And what else? Radius is 5. Okay, so radius of that charge is equal to 5 cm. And the point is located at 8 cm. Okay, away from the center of the charge. Okay, so in this case, so the radius of the charge is equal to A. Okay, so that means that in this case, instead of A, so we can replace it with 5 centimeter. This one is 5 centimeter. Okay, so and then we need to find the D, okay, at 8 centimeter from the center of the charge. So in this particular case, so we know that the 8 centimeter is located outside from the charge. So in this case, so we just put all the parameters we know. So the vector of D is equal to rho v a to the power of 3, so divided by 3 r squared. Okay, so coulomb per meter squared. Okay, so we have the rho v is equal to, the value of rho v is equal to 5 microcoulomb per meter power of 3. Okay, so multiply by A to power of 3, right? Okay, A is 5 centimeter, so 0.05 is the power of 3. So divided by 3, and the value of R is equal to 0.08 to the power of 2. Then if you solve it, calculate also by using the calculator, then you get the answer lah. Okay, in term of how many coulomb per meter, meter square. Okay, so we move to the tutorial 4, question number 3. Alright. So a coaxial resistor of length L consists of two concentric cylinder. The inner cylinder has radius A. It made of material with conductivity sigma 1. At the outer cylinder extending between R equal to A until R equal to B, and made from a material conductivity equal to sigma 2. If the two ends of the resistor are kept with a conducting plate, so that the resistance is given in this question. Alright. So in this case, so we have two conductors. Right? So we have, this is the first conductor, and then we have the other conductor, this position. Okay. The radius for the inner conductor is equal to A, and the radius for the outer conductor is equal to B. Okay. So for the inner conductor, so we have conductivity is equal to sigma 1. And this one is inner. Right, inner. So the outer cylinder is having sigma is equal to sigma 2. This one is for the outer conductor. Alright. So in this case, okay, so it provides us another information that the inner and outer we kept together. Right. So if we kept together the inner and outer conductor, so we will have the equivalent circuit for this is something that like this. Okay, so we have R for inner, is parallel with us R on the outer cylinder. So this is our R total. So in order to calculate the total resistance, so we can use this formula. 1 over RT, R3 is equal to 1 over R inner plus with 1 over R outer. Okay. So then we need to determine on it, we need to develop the expression for both resistance. Okay. So from general expression for the resistance, right? So we have R is equal to L divided by sigma A. Okay. If we consider the inner conductor, so we will have R inner. So the length of the conductor is given as L. L divided by sigma 1, okay, which is the conductivity for the inner conductor. So multiply by A. So A is given here is equal to pi A squared. Okay, so this one for the resistance for the inner conductor. For the outer, so R outer is equal to L, so divided by sigma 2. Okay, so this is the conductivity for the outer conductor. Okay, so multiply with the area. So this time the area will be pi R squared. So for in this case, so the cross-sectional area for the outer conductor is this area. Okay, so we need to calculate the total area. So minus with the area of in the conductor. So that's why in this particular case we will have d squared. So minus d squared. Alright. So if we put all the equation together, so we will have uh, equation like this. 1, so divided by R3, RT, okay, total of resistance is equal to 1 over R inner. So this one. So he will get this equation will be like this. So sigma 1 pi a squared, so divided by L. So plus this expression. So we have sigma 2 pi a squared minus a squared. So divided by L. So we will have if we can factorize the pi, so sigma 1 a squared plus sigma 2 a squared minus a squared. So divided by L. Okay. Then if we want to find uh, the R3 here, so we just inverse this equation. So we will have R3 here. Okay, if we inverse, then so this part will become our denominator. Pi sigma 1 a squared plus is sigma 2 a squared minus a squared, and the top will be L. Alright, so supposed to the same as the expression that we need to find. So today for question number 8. Okay, so basically I have upload the detailed explanation for this solution. Okay, in the YouTube. Okay, so basically when we have the boundary condition as given in that question, okay, so we have a several layer of I guess this is dielectric, okay, and each dielectric layer have their own specific value for the electric permittivity epsilon, okay, epsilon 1 until epsilon 3. Okay, so the general equation, okay, that we need to consider in order to solve this. Okay, so we will have okay, so we will have the ratio of tangent theta 1 divided by tangent theta 0 is equal to 1 divided by epsilon 0. Okay, so that means that this side of this equation, okay, so will involve with one medium. So let's say this is the medium. In this case, so let's say the medium governed under epsilon 1, for example. Okay? So by referring to the question. So on this top equation will be involved with the parameter that having in the medium that governed by epsilon naught. Okay. So based on the this expression, then we can have. So let's say we want to find the theta 1, for example. So governed by the medium with the electric epsilon 1 is equal to 3 epsilon naught. Okay. So based on this argument, so we will have inverse tangent. Okay, so tangent theta naught, which is this is the angle that exists in the air. Okay, so multiply by the ratio of epsilon 1, so divided by epsilon naught. Okay, then if you put all the information, so tan inverse tangent minus 1. So tangent naught is the 45 degree, okay, based on what has been given in this in the question. Okay, epsilon 1 is equal to 3 epsilon 0. Okay, 3 epsilon naught. So divided by epsilon naught. Okay, so if we solve it together, then we will have the angle of E, okay, between the vector of E and the Z inside medium that having permittivity is equal to 3 epsilon naught, so is equal to 71.56 degrees. Okay. So for detailed solution for this, so you may check on the video. I think this is maybe from the live tutorial, if I'm not mistaken. Or you may check it, which one with the video that I mentioned. Okay. So this is the angle that result in a material which is have epsilon 1 is equal to 3 epsilon naught. Okay. For the next layer, so we want to find the theta 2. Okay. So theta 2 is under material with having epsilon 2 is equal to 5 epsilon naught. Okay. So the similar equation that we will apply. So inverse tangent theta 1 multiplied by the ratio of epsilon 2 divided by epsilon 1. So inverse tangent. So tangent 1, theta 1 is this. This is the value for the theta 1. So we have 71.56 degrees. So multiply by the ratio epsilon 2. So epsilon 2 is equal to 5 epsilon naught. So divided by 3 epsilon naught. So the solution of it we will have is equal to 78.70 degrees. Okay. So for the theta 3, solution for the theta 3, which is the angle that consists in epsilon 3 is equal to 7 epsilon naught. Okay. So the same again. So we need to perform inverse tangent theta 2 multiplied by the ratio of epsilon, this one should be epsilon 3 divided by epsilon 2. Okay, and the angle for theta 2 is equal to 78.70, and epsilon 3 is equal to 7 epsilon naught, so divided by 5 epsilon naught. Okay, so if you solve this one, then we will get 81.80 degrees. Okay, if you extend the solution to the theta 4, okay, so theta 4 is the angle that we have in the lowest layer of air, right? So we will have inverse tangent of theta 3, so multiply by E naught, so divided by T3. Okay, so tangent, so theta 3 is equal to 81.87 degree. Okay, so multiply by epsilon naught, so divided by epsilon 3 is equal to 7 epsilon. Okay, if you solve this one, basically we get the same answer as the initial one, is equal to 45 degrees. Okay, so basically this question is start with some derivation. Okay, so how to derive the angle or the ratio between angle between one layer to another. Then in the end, so from that derivation, so we will have this ratio. Okay, and then from this ratio, then we can work out in order to find the angle at any medium that the question asks. So for detailed explanation, I think maybe you can refer to the video lah. I think that one in that particular video, I explain one by one in terms of how to derive that ratio. So tutorial 4, question number 5. Alright, so a cylinder shaped carbon resistor is 8 centimeter in length and its circular cross section has diameter of D is equal to 1 mm. Alright, so we have one cylinder of a conductor. Alright, so the length of it is equal to 8 centimeter. And the radius of it, but in this case, it gives us in terms of diameter. Alright, so the diameter is equal to 1 millimeter. So we need to find the resistance. Okay, so first, so we should know the standard expression for the resistance. So L is equal to L, so divided by sigma A. Okay, then we need to find the value for the sigma or the conductivity for this is carbon resistor. If you look into or if you Google it, then the value for conductivity for carbon is equal to so sigma for carbon is equal to 3 times 10 to the power of 4 Siemens per meter. Okay. So we know that the length is equal to 8 centimeter is equal to 0.08. So sigma is equal to 3 times 10 power of 4. And the cross-sectional area for this conductor is equal to pi multiplied by the radius is power of 2. So the radius is the diameter is equal to 1 mm. So the radius will become 0.5 times 10 power of minus 3. Okay, power of 2. Okay, so we just divided the diameter with apa nama? Setengah mm lah. So 0.5 mm. So by solving this one, so we will have the answer for this resistance is equal to 3.4 ohm. Okay. So this one is quite straightforward lah. Straightforward. Okay. And for the B to reduce its resistance by 40%, so the carbon resistance is put with a layer of copper of thickness of T. Use the result of Q3 to determine. Okay. Q3 itu basically we need to derive the expression. If we have one conductor and we coat the conductor with the other material, so we need to find the total resistance. Okay, so basically the answer has been given in that particular question. Okay, so in this case, the same carbon resistor. So this is our carbon resistor, and then we coat it with copper at the outside of it. Okay, then we coat with copper here. So we still have the same length here, is equal to 8 centimeter. So the diameter of it is still the same, 1 millimeter. And the question asks us to find the thickness of this copper layer, right? Okay. So based on the question, the answer given in the question number 3, right? So in order to calculate the resistance, if we have this condition, so we will have R is equal to pi sigma 1 A squared plus sigma 2 B squared minus A squared, and here we have L. Alright, so we know that the sigma 1 will be represent the value for the carbon. Okay, and the value we have been searched just now is equal to this value. And the sigma 2 in this case should be the conductivity that represent conductivity value for the copper. Okay, if we refer to the appendix, the conductivity of copper is equal to 5.8 times 10 to the power of 7. Okay, then this is the radius for carbon. Okay, and this is the radius for copper. Okay, basically we need to find this radius first. Okay, so in terms of radius, so in terms of resistance, so we say that we need to reduce the resistance by 40%. Okay, so that means that the R new that we need to find is equal to total 40% reduction is equal to 60% of its original resistance. Okay, so 60% multiplied by 3.4 ohms, and how much that we get here? So basically, we will have 2.04 ohms. Okay.
Yes.
So we replace this value of resistance into this expression. So we have 2.04 is equal to, okay, so pi. So sigma 1 is equal to 3 times 10 power of 4 multiplied by, so the radius for the carbon is equal to 0.5 times 10 power of minus 3, okay, with the power of 2. So plus sigma 2 is equal to this value, 5.8 times 10 power of 7. Okay. So B squared, so the value that we want to find, and A is this value. Okay, 0.5 millimeter. Okay, so pula ruang kan. Okay, so the length of it is equal to 0.08. Okay, so by solving this one, so we will have the value for B is equal to, saya dah jawab ni. Berapa dapat? So if you calculate, so how much that the value of R that we should have? So this one. So the B that I calculated before, so I get the value for B is equal to 5.00086 times 10 power of minus 4 meter. Okay. Basically, it's almost 0.5 mm lah. Okay. So then, so we need to find the thickness. Okay, the thickness of the copper wire, the copper layer lah. So T is equal to B minus VA. So B is 5.00086. Okay, so minus 5, okay, times 10 power of minus 4. So we will have the answer is equal to 0.0086 micrometer.